Welcome back to today's video. Today, we are going to uncover the mystery behind a very special leaf. A leaf that's actually found in muddy, stagnant conditions, but is always remarkably clean. A leaf that does not allow water to actually sit on it. What is this? Let's find out. Have you heard of water-repellent surfaces? Well, then you must have also heard of water-resistant surfaces. And what about waterproof surfaces? Although these three terms sound similar, they are absolutely different. So now let's make a distinction between water-repellent, water-resistant and waterproof surfaces. Let's kick off with water-repellent surfaces. What happens when a few drops of water fall on the protective screen of your smartphone? They do not penetrate inside and destroy the electronics. No, they simply form small beads. Basically, they come together, and if you shake the phone off, they just fall off the phone and your phone is dry as before. That is an example of a water-repellent surface, something that does not allow water to penetrate through it, and instead water has a tendency to basically roll off that surface. One thing, however, to note for water-repellent materials is that if you submerge them in water for prolonged periods of time, in that case, they actually may allow water to penetrate, but as long as it's just a few drops of water, they will totally repel water and cause it to roll off the surface. With this in mind, let's move on to water-resistant surfaces. Water-resistant surfaces are those that can withstand water for some duration of time but eventually allow water in. Let's take an example of something like a fitness tracker that you probably wear on your wrist. It's exposed to the sweat on your skin throughout the day, but this sweat does not penetrate the watch and destroy the electronics. But if you were to take that device and place it in a beaker of water for a good amount of time, it would eventually get destroyed. The electronics would be spoiled. That is what a water-resistant material is. It can hold off water for a greater period of time as compared to a water-repellent material when submerged, but eventually it does let water through. The final case is that of a waterproof material. For this case, take something like an action camera that is used to shoot scenes like in scuba diving or for underwater activity, basically an underwater camera. In this case, the camera remains submerged in water for great periods of time and still is not destroyed. It is made up of waterproof materials that even on prolonged exposure to water and prolonged exposure to depths of water still do not fail and do not allow water to penetrate. And with that, we've made a distinction between the three different words: water-repellent, water-resistant, and waterproof. Our focus for today is on water-repellent materials. And now it's time to unveil our mystery object, the lotus leaf. To understand what makes the lotus leaf so remarkable, let's compare it to something far more ordinary, like a slab of glass. So take a slab of glass and a lotus leaf and place a few droplets of water on each of them. In the case of glass, you will observe that the water droplets tend to spread out on the surface. However, in the case of the lotus leaf, the water droplets tend to pull themselves together into these tiny beads that have a tendency to easily roll off the surface. Now, the water wasn't different in both cases, so the difference must be in the type of surface. And to understand what this difference is, we first need to understand what happens when two materials come into contact. When two materials come into contact, there are two different types of forces that come into play. The first force is known as a cohesive force. This is the force between molecules of the same material. So in our case, it's the force between the water molecules themselves. The second force is known as an adhesive force. This is the force between molecules of different materials. So in our case, it's the force between the water molecules and the molecules of the surface on which the water droplet was placed. Now, these two forces are actually competing against each other, and whichever force wins decides the shape that the water droplet will take when it falls on that surface. So let's start with the first case. What happens when the adhesive forces, that is the forces between the water droplet and the surface, are greater than the cohesive forces, that is the forces between the water molecules themselves? What happens then? In this case, such as in glass, the water droplet has a tendency to spread out over the surface. These surfaces are known as hydrophilic or water-loving surfaces. A great way to understand how well water comes in contact with a given surface is through a parameter known as the contact angle. To visualize this, imagine a line drawn at the surface and another line drawn at a tangent to the edge of the droplet. The angle between these two lines is known as the contact angle. And for hydrophilic materials, this angle varies from between 0 degrees to 90 degrees. If the angle is lesser, say if the angle were around 0 degrees, the water would be completely spread out on the surface. And as the angle increases, the tendency of water to spread on the surface decreases. In other words, a lower contact angle means that water tends to spread out on the surface more. But what happens when the cohesive forces are greater than the adhesive forces? In this case, such as in the lotus leaf, the water droplets have a tendency to sort of bead up. In other words, they form this sort of rough spherical shape. Such surfaces are known as hydrophobic or water-hating or water-fearing surfaces. In such cases, the contact angle is greater than 90 degrees. But you know what's amazing about the lotus leaf? It does not just repel water. It is extremely water repellent. In fact, it belongs to a special class of hydrophobic surfaces known as superhydrophobic surfaces. So, what's exactly happening in the lotus leaf? Whenever a water drop falls on the leaf of a lotus, it does not just bead up. It also has a very great tendency to roll off the leaf on the application of the slightest force. Something like maybe when the leaf is tilted or when a gentle breeze blows by. And that's not the end of the story. Every time a water droplet rolls off the lotus leaf, it carries away with it a small amount of dust and dirt that was present on the leaf. In other words, every water droplet acts like a tiny cleaning machine for that lotus leaf. And this self-cleaning effect of the lotus leaf is what came to be called as the Lotus Effect. But what exactly is the Lotus Effect? Why does the lotus leaf particularly show this effect? To understand that, we have two main factors. The first is the chemistry of the leaf and the second is the architecture of the leaf. So let's dive right in. Starting with the leaf chemistry. A lotus leaf tends to produce a layer of waxy molecules that naturally cover its top surface. Now, wax is a hydrophobic substance. So whenever water falls on the surface, this waxy layer naturally has a tendency to repel that water. Even before we go into the leaf architecture, this is already the first level of protection of the lotus leaf from any incoming water. Now let's move on to the architecture of the leaf. What do I mean by that? Well, have you ever felt a lotus leaf? It must have felt sort of smooth to you. But take that same leaf and place it under a microscope. Zoom in and it's a completely different picture. In fact, the surface of a lotus leaf at a microscopic scale is not smooth at all. It's covered with multiple bumps and undulations on the surface. In fact, the bumps on a lotus leaf are layered. That is, you have one layer of bumps and you have a second layer of bumps over those first layer of bumps. So let's give these layers names and understand how exactly each layer helps to prevent water from staying on that lotus leaf. The first level of bumps is known as the microscale level bumps. since these are microscopic in size. To understand how these actually help the leaf, let's imagine two surfaces. One is a flat surface and one is this bumpy surface. Place sort of a water drop on each of these surfaces. What you observe is that because the water drop is not a complete sphere, the area of contact in case of the flat surface is greater than the area of contact when it is placed on these bumps. Also, these bumps have sort of an air cushion between them and under that water drop. This is what gives the lotus leaf its spongy effect as well. Moving on to the next layer of bumps, they are nano-sized. In other words, that layer is a nanoscale layer. The main function of that second nanoscale layer is that it contains waxy crystals. These wax crystals basically reduce the friction between the water droplet and the lotus leaf and make it easier for the water droplet to roll off the lotus leaf. A combination of these bumps is what enables the lotus leaf to actually display its superhydrophobic nature. So, in reality, the lotus leaf isn't as smooth as it looks. It actually is rougher than we could ever have imagined. But the next important question is, how is this relevant to our real-world applications? When engineers look at this, is there a new product that they can actually come up with? And believe me, for centuries, no one actually thought of any concrete applications. We observed this phenomena of the lotus leaf in nature for a really long time. But it was only when scientists discovered that the lotus leaf has a special superhydrophobic property that engineers were able to develop applications for it that are now widely used in our daily world. So let's look into some of those examples. We can understand these examples in a couple of different categories. The first one is an application similar to that of the lotus leaf, to prevent dust and dirt from sticking onto surfaces. This can be further used in two ways. One, in the term of paints that are used on buildings to prevent dust and dirt from sticking onto the buildings. The second is in terms of textiles. So we have clothing these days that employ this lotus effect, and as a result of that, the clothes remain cleaner for longer and are also easier to maintain. The second category that we can talk about is in case of electronics. The lotus effect is used in case of sensitive electronics and develop materials that are actually repellent to water and hence protect those electronics. The third example is that of metal corrosion prevention. Metal corrosion is a huge problem because it not only leads to a lot of danger, but it's also very expensive. And special types of coatings and materials are being developed that can be applied to metals to prevent them from rusting so quickly. The final application is something more unexpected than you would imagine. It's in airplanes, and more specifically on airplane wings for airplanes that fly in really cold conditions. The picture is this. When an airplane flies in a really cold condition or a weather condition, ice tends to accumulate on the wings of the aircraft, and this can be detrimental to the life or the safety of the aircraft. For this purpose, organizations such as NASA and Airbus are researching or have developed certain materials that can actually prevent this accumulation of ice on the wings of the aircraft to ensure a safe flight and a better life for that particular aircraft. In the end, this story isn't just about the lotus leaf, because if you took a lotus leaf and looked at it right now, it would look pretty ordinary to you, up until the point you actually put it under a microscope and observed its surface. From this we understand that observing or changing something microscopic even can have a great impact and can in some cases completely transform the way our macroscopic world behaves. If this video sparked a new perspective. I'd love to hear your thoughts. Do drop your comments, questions, and ideas for future topics below. If you found it valuable, please like, share, and subscribe. Looking forward to seeing you in the next video.